Thank you very much. And first of all, I want to thank all of organizers for invitation and for financial support. So this work was made with collaboration with my supervisor Evgeny Kochetov and also with Alvaro Ferros from International Institute of Physics. So and today I will tell about CPT study of the Fermi-surface reconstruction in the TG model. Is it work? No. Okay. So a brief review of cuprates. A brief review of the cuprates. So I think all of you know about it much more than I. So cuprates is some kind of some kind of metal which contains the cuprum oxide planes, which also correspond to the superconductivity. So and this is very very famous type of compounds because it has a lot of mysterious phases. So I should note the antiferromagnetic phase, which present at low doping. So and actually at overdoped regime, the cuprates demonstrate the Fermi liquid behavior, which contains the Fermi liquid-like cylinder, so Fermi-surface. So, but more mysterious phases is present in the underdoped regime. So it's superconductivity, of course, and one more is the pseudo-gap phase, which characterized by by the Fermi-surface, which do not contain the close pocket, and this is a disconnected arc, and this this behavior is absolutely unexpectable from the Fermi liquid theory. So to solve it problem, it's a very very important task. So, but the new stage of the investigation of the cuprates was started by discovering the quantum oscillation, which was made by Dario and Liard in 2007. So quantum oscillation implies that the Fermi surface, which expect to be arcs, which not closed. So quantum oscillation implies that the Fermi surface becomes closed pocket, and this pocket have a much smaller area than the Fermi liquid like cylinder. So moreover, the further discovery of the change of the sign of the Hall and Zibig coefficient revealed that this pocket should be electron-like, which absolutely unexpected, and this behavior is appears to caused by translation symmetry breaking, which also is present in the cuprates. So yeah, and charge ordering was also found in the cuprates. So, but it would be too easy to have one ordering. So in the different types of cuproids, present two general type of ordering. It's the stripe order and checkerboard order. First of it is present in E3 Bari cuprum oxide, in lanthanum strontium cuprum oxide, and checkerboard is present in other types. Sorry, I can't name it. So, but the general properties of this ordering is the length of the modulation vector, which is also 3 or 4 lattice spacing in all types of cuprate, in all compounds. So, moreover, in the E3 Bari cuprum oxide, which is the most popular and most important cuprates, also present two type of ordering. It's two-dimensional ordering in zero magnetic field, but in high temperature, and three-dimensional ordering in high magnetic field. So it's also some kind of, puzzle. And due to this, the phase diagram of the cuprates can be shown like this one. So we have a pseudo gap, we have a superconductivity, and inside of this we have a charge density wave dome, which also located near, which starts from about 8% of doping and finished at about 16%. The phenomenology approach in describing this this phenomena is mostly based on the tight banding model, which is right in here. So the first achievements in this, the first achievements in the calculation of electronic pocket, which is should present in the cuprate, was made by Harrison and Sebastian in 2011. So, and they used the multiply co-ordering to calculate the band structure and the Fermi-surface, and it was first observation of electronic pocket in the direct calculation. But all of this approach is based on the including some long-range ordering term by hand. So we have to exclude external term to the Hamiltonian to break the symmetry and to make some charge ordering. So and we can choose this value of p, so this function. It's a function, so we can choose it such way as we want, but to correspond the experimental data to correspond the electron pocket, we should choose it like a D wave form factor with charge density wave. So the further calculation of Fermi-surface in the framework of this approach was made by Elias Chapthari Sajdev, and they calculated the Fermi-surface with accounting the bound density wave, and they get the electron pocket with two small hole pocket. So it's also predicted by Harrison and Sebastian. So they predict that this Fermi-surface is can exist, but it's not it's not a real Fermi-surface as they said. So At this moment, there are two opinions about the presence of hole pockets in the Fermi-surface. So, to be honest, we can say that they exist or not. So it's an open question. So, our model we also based on the tight binding model, but we do not include any longer range ordering term by hand to the model. So, and this way we should broke the translation symmetry, and we broke it by enlarging the translation vector, which is unitary on the 2D square lattice, and we set it to we set the length of the translation vector to 3. So and this way the translation is conserved only for the 3 by 3 cluster, and it's broken in another way. So you can see that in this way we can translate this cluster to the new by the new translation vector, and we get a good agreement. Further step is dividing the Hamiltonian to the intracluster part and the intercluster part. So the intercluster part is also tight binding model, which describes the hopping only between the clusters. So all hopping inside the cluster are included in intracluster term. So you can see it here. So and in this way, if we don't modify anything, we just get a simple tight binding model with large Fermi liquid-like cylinder as a Fermi surface. So we add the Hubbard term to the intracluster part, which correspond to the strong Coulomb repulsion, which is also observed in the cuprates. So and we put U is very large value, so we can replace the Hubbard model inside the cluster to the TG model. And in this case, we have a constrained fermion creation and annihilation operator. So, and we also have a spin-spin interaction. And this way, the following approach is based on this scheme. So we have a 3 by 3 cluster as a new unit cell, and we have a intracluster interaction which is described by this part. So we use the cluster perturbation theory for calculate the band structure of this model. So the first step of this is exact diagonalization of the intracluster part. So it should be noted that the TG model contains only the 3 states per site. So it's the empty electron with spin up and electron with spin down. However, in the 3 by 3 cluster, we have about 20,000 states per cluster. So following calculation becomes fully numerical. So we can treat it. We cannot treat it analytically. So we have to use numerical calculation. So yeah, and this way the intercluster Hamiltonian becomes the matrix with this size. So, and we should diagonalize this matrix. We have to calculate eigenstates, so a whole set of eigenstates. And other we move to the new basis, which based on this eigenstates of clusters. So, and we we write the Hubbard operators based on this eigenstates. This way we replace the cluster which contains the hopping some hopping term to the cluster which contain only the diagonal term, but it contains more complex inner structure. So following step is transition to this new basis in which the intercluster parts becomes diagonal, and intercluster part we should transform to this new basis. So in this way, and as a result, we get the Hamiltonian. Write it here. So third step is the Dyson equation, which we have to solve. So okay, I have not a lot of time, so we have to solve, and we restore the green function of we restore the electron green function, and we calculate the spectral weight, and we can calculate calculate the Fermi-surface as an orbit of quasi-particle, and calculate the Fermi-surface with accounting the spectral weight distribution. So yeah, it should be noted that 3 by 3 cluster is large, but not enough to have some problem with this. But we actually cannot take the larger cluster because it's too long to calculate it. It's just too complex. So okay. The diagonalization of the clusters leads to the ununiformly distribution of the charge inside the cluster. So this way we can get this this picture of the charge distribution. So you can see that this pattern looks like a checkerboard pattern. So but in this way we pin the length of the charge density wave modulation vector. So and the length of this is free because we have a free site per 1 month. So it should be noted that in Itri-Barry Cooper-Mach site, the modulation vector is length of modulation vector is about 3.2. So we restrict it to integer value, and we set it free. So it's it's a good agreement with experimental data. Fermi-surface, which was calculated by this method, you can see here. So this is a Fermi-surface calculated by cluster perturbation theory with accounting the Coulomb repulsion, and you can see the evolution of the Fermi-surface. So at the 8% doping, we have closed hole pockets. So hole pocket this and translation of this. So, but while we increase the doping level, the Fermi-surface undergoes the topological transition. So Fermi-surface becomes electron-like, more the hole-like. So and it occurs at about 9%. Moreover, with further increase the doping level, we can calculate that the Fermi-surface will contain the hole pockets in addition to the electron pocket, which located in nodal region. So and this whole evolution was calculated by constrained electron plus Coulomb repulsion, and here you can see the results calculated from unconstrained electron in the framework of type binding model with long-range ordering. So it's the most famous results of calculation the Fermi-surface, where you can see the electron pockets located in the nodal region, and also electron pockets plus Hall pockets. Next step is calculate the Fermi surface with accounting the distribution of the spectral weight. So you can see the previous Fermi surfaces here, and we can actually we can remap some spectral weight. So it's look like a pseudo gap distribution, which mapped on the CDW phase Fermi surfaces. So, and the result is presented here. It's the Fermi surface at the 8% doping. So, which looks like a pseudo gap. So there we have a topological phase transition, electron pocket and electron pocket plus 2 small Hall pockets. So we can compare this result with the RPS data. This first and second pictures correspond to the RPS data, and next evolution of this of the Fermi surface is correspond to the Harrison and Sebastian theory proposed to describe the existence of the open-net electron pocket, which also have a diamond-shaped form. So, and also there's a question about electron pocket plus 2 Hall pockets. So actually, electron pocket plus 2 Hall pockets can be reproduced in the framework of bound density wave, and in the presence of some Coulomb repulsion calculated by mean field approach. But there are one important difference between our result and between the result calculated from tight bonding approach, so Fermi liquid based theory. So in our approach we have no spectral weight, we have 0 spectral weight in the antinodal region, so it corresponds to the pseudo gap Fermi surfaces correspond to the data obtained by RPS, and it corresponds to the theory of the pseudo gap, but in another way. So in the case of model based on the tight bonding without Coulomb repulsion, we have a additional branch in the antinodal region, which correspond to the Fermi liquid cylinder, which also does not present in the RPS data. So also we have the same CDW modulation vector. So this vector connects the breakpoint of the Fermi surface. The further step is the calculate the spectral weight distribution around the Fermi surface. So we can make a free slice of the spectral function in these directions. So the first directions is across the electron pocket, and you can see that gap lies above the Fermi level. Second slice is cross the breakpoint, and you can see that it's breakpoint. At the breakpoint gap is opened. So, and third slice correspond to the Hall pocket, where the gap lies above the Fermi level. So, and we can conclude that the strong Coulomb repulsion leads to the gap opening in this case. And moreover, we can conclude that the value of this gap is linearly dependent on value of column repulsion. So in the case of we set U equals to 0, the surface becomes the large Fermi liquid-like cylinder. Fermi-surface structure can be reproduced here. So this two main two main figure represent the structure of the Fermi surface with including the doping level. So this Fermi surface is the okay. It's it's too difficult to me. Each slice of each horizontal slice of the Fermi surface correspond to the Fermi level, the corresponding doping level. So and its distribution by the angle phi. So and angle phi you can see here. So we can see the opening of some anisotropic gap in the band structure. So and this anisotropic gap is caused by strong column repulsion. So and actually here you can see the forming of the hole pockets and electron pockets, and further evolution of the Fermi surface when it becomes a large Fermi liquid-like cylinder. So yeah, I have no time. The last slide is density of states and sign of carriers. So we calculate the density of states at the Fermi level, and also we calculate the effective mass of the carriers on the Fermi level. So to be honest, we calculate only the sign of effective mass because it's too, it's we have not enough accuracy to calculate the effective mass. So we can calculate only the sign of it. So and here you can see the two critical doping level of the CDW phase. First of it is 8.5%. So it's the point where the CDW phase is starting, and the second is where is the finishing. So and also we know the CDW one more. It's not a phase transition, but it's a special point where the electron pockets becomes the electron pockets plus two hole pockets. So in this picture you can see the distribution of the density of states at the Fermi level, which depicted in black, and also in blue depicted the density of states associated with hole carriers, and in red with electron carriers. So you can see that there is a drop of the hole conductivity and rise of electron conductivity, and the doping range, which fully correspond to the expected electron pocket. So and also we calculate the value of the gap, which is also correspond to this phase diagram. So to conclude, I can say that we can compare our result with the experimental observation, which predict the value of the CDW starting at 8%, and second critical doping is about 16%. So to be conclusion, I can say that we calculate the Fermi surface reconstruction. So we calculate the Fermi-surface reconstruction with in whole range of doping, not only in the CDW phase, and we calculated with counting only the strong Coulomb repulsion without any long-range ordering term, and without including any, any other term which helps to form in the CDW phase. So only the one phenomenological parameters which is included in our model is the length of the CDV modulation vector. So, and we can conclude the Coulomb repulsion is responsible for the forming of the Fermi-surface reconstruction in the cuprates, and also we can say that the both the electron pocket and the electron pocket plus two hole pockets can be present in the cuprates in the differing doping regime. So yeah, and I think that's all. Thank you for your attention. Yeah. And
Okay, so